Hello everyone, I'm Amit K. Jain, working as Assistant Professor in STM Institute of Technology, Ujure. Welcome to today's control system session in relation to Module 4, Stability Analysis. In today's session, we will be learning about the topic root locus. We will quickly go through the problem statement. Sketch the complete root locus of the system having open loop transfer function g of s into h of s is equal to k divided by s into s plus 1 into s plus 2 into s plus 3, and also comment on the stability of the system. Step 1 is identify poles, zeros and branches. So now what are poles, what are zeros and what are branches? Here we have our open loop transfer function which is having a numerator and denominator. The roots of the denominator of the transfer function are called as system poles. The roots of the numerator of the transfer function are called as system zeros. So now here in the denominator we have four roots. At s is equal to 0, at s is equal to minus 1, at s is equal to minus 2 and at s is equal to minus 3. So we will be having four poles, poles represented by p is equal to 4. Since we have four roots in the denominator, we will be having four poles located at s is equal to 0, s is equal to minus 1, s is equal to minus 2 and s is equal to minus 3. Here in the numerator there is no term related to s, so there will be no roots. So number of zeros represented by z will be equal to 0. Now coming to branches, number of branches will be equal to either p or z, whichever is greater. Here p is greater than z, therefore number of branches will be equal to 4. Number of branches is represented by p, so n is equal to p is equal to 4 since p is greater than z. Now with respect to branch, we have to identify for each branch starting point and terminating point. General theory states that a branch will always start at an available pole location and should end at 0. But if there are no 0 locations available, they will end at infinity. So here in this particular problem, we have 4 branches, right? So all the 4 branches will start at the available pole locations, and they should have ended at 0, but there are no 0 locations available, so all the 4 branches will start at the 4 available pole locations and will end at infinity. So step 2 is plot the pole 0 plot, identify root locus bar no root locus region, predict breakaway point. So we will start by plotting the pole 0 plot. The pole 0 plot is plotted on the S-plane. S-plane is nothing but a two-dimensional space where you can plot a complex root. Your x-axis is nothing but real axis represented by sigma, and y-axis is nothing but imaginary axis represented by j omega. In the x-axis you can plot the real numbers, and in the imaginary axis you can plot the imaginary numbers. So now we will plot the poles. We have a pole at s is equal to 0. Then we have a pole at s is equal to minus 1. Then we have a pole at s is equal to minus 2. Then we have a pole at s is equal to minus 3. There are no zeros. So now we will identify the sections on real axis for whether they are root locus or no root locus. So now what we have to do is, we have a real axis, right? So the sections on the real axis, whether a particular section is root locus or no root locus, that needs to be identified. So how do we identify that? So here we will consider this section now, that is the section which is to the right of the point s is equal to 0. So now we need to identify whether this particular section is root locus or no root locus. So for that what we have to do is, we have to count the total number of real poles and zeros to the right of this section, and if it is 0 or even number, then it is a no root locus region, and if it is an odd number, it is a root locus region. So here you can observe, to the right of the point s is equal to 0 there are no poles and zeros. That means the total number of real poles and zeros here is 0. That means the conclusion is no root locus region. Now similarly we will consider the next section. between 0 and minus 1. So now again to the right of the point s is equal to minus 1, we have only one pole, there are no zeros. So in totality we have one pole, which is an odd number. So if it is an odd number, then the conclusion is that particular section is root locus. So now we will shift our attention to the next section between minus 1 and minus 2. Again, if you count the number of poles and zeros to the right of the point s is equal to minus 2, here you have 1 plus 1, 2 poles. Again, 2 is an even number, and if it is an even number, what is the conclusion? That particular region is no root locus. Now similarly, we will consider the section between minus 2 and minus 3. So now with respect to the right of the point s is equal to minus 3, you have to count how many number of real poles and zeros are there. Again, 1, 2 and 3. Since we have 3 poles to the right of the point s is equal to minus 3 and 3 is an odd number, this particular section between minus 2 and minus 3 is considered as root locus. Now similarly, we need to find the section to the left of the point s is equal to minus 3, whether this is root locus or no root locus. So for that, what we have to do is, we will consider an imaginary point somewhere over here in the section, and to the right of this point we will add the number of real poles and zeros. So here we have 1, 2, 3 and 4, and 4 is an even number. Since it is an even number, we can safely conclude that this particular region is no root locus. So now we will predict the breakaway points. So to predict the breakaway points, what we need to do is we need to plot the movement of poles on the real axis, and that is where identifying regions as root locus or no root locus will help us, because a pole will move on the real axis only in the root locus region. If it is a no root locus region, movement of the pole is prohibited. So now here you can observe there is a pole at s is equal to 0. This pole on real axis, it has two options. It can either move towards left or it can either move towards right, but it cannot move towards right because it is a no root locus region, so it will move towards left. Similarly, you have a pole at s is equal to minus 1, which is also having two options. It can move towards left or it can move towards right, but it cannot move towards left because it is a no root locus region, so it has to move towards right. So now if you observe carefully, they are moving towards each other, right? So at some point they have to meet. The point where they meet is called as breakaway point. So here we can predict that between 0 and minus 1 there is a possibility of breakaway point. Similarly, we have a pole at s is equal to minus 2, right? And it cannot move towards the right because it is a no root locus region, so it will move towards left. Similarly, we have a pole at s is equal to minus 3, which cannot move towards left because it is a no root locus region. It will move towards right. And again, they are moving towards each other, and at some point between minus 2 and minus 3, they are going to meet each other, and that point where they meet each other is called as a breakaway point. So here we can make one more prediction that between minus 2 and minus 3, there is one more possibility of a breakaway point, B2. So the general prediction is that the minimum number of possible breakaway points for this particular system is 2. B1 between 0 and minus 1, B2 between 2 and minus 2 and minus 3. So now this is step 1 and step 2. The rest of the steps we will see in the next video.